Now let me consider this problem. If f equals to x square plus y minus 4i plus 3xyj plus 2xz plus z square k, evaluate del cross f dot n ds, where s is the surface of the sphere, x square plus y square plus z square equal to a square above xy plane. Let me first draw the surface. This is surface of the sphere which lies above xy plane. So this is an open surface. I'll draw it first, then I'll discuss. So here f is x square plus y minus 4 plus 3xyj plus 2xz plus z square k. This is the surface. This is surface over which we have to evaluate the surface integral. We have to evaluate the surface integral over surface of the sphere which lies above xy plane. So this is the part of the sphere which lies above xy plane. So the part of sphere which is above xy plane will be an open surface. As I told you earlier, Gauss Divergence Theorem holds for the closed surface. So in evaluation of this surface integral, since the surface integral has to be evaluated on the open surface, I can't apply the Gauss Divergence Theorem, because this S is a hemisphere, it is a part of the sphere lying above xy plane, and this part is open. This part is open. So we have to evaluate del cross f dot nds over an open surface. Over an open surface, I can't apply the Gauss Divergence Theorem. But if the surface would have been closed, means if the surface would have been closed, how can you close the surface? By adding a base to it. If the surface could have been closed, it would have been very good. Why? Because if the surface would have been closed, this would have been equal to del dot curl of f deta, and del dot divergence of this curl of f is always 0. If the surface would have been closed, this is not, but if suppose imagine the surface would have been closed, this s would have been this plus the base, in that case this could have been equal to del dot del cross f deta, and this is always 0. But unfortunately the surface is not closed, the surface is open. But we have a hint, we can get an idea from here that if suppose I consider, if suppose this is a very important type of problem, this usually comes in every exam. Here this is an open surface. Now let me consider from here we get an idea that if anyhow we make this surface closed, the integral would have been 0. So let us consider a closed surface sigma consisting of spherical part S, and let me call this base as S dash, and is spherical, I will call it a hemispherical part, and its base S dash. So sigma here consists of S and S dash. Sigma consists of hemispherical part and the base. It means sigma is a closed surface, and on this closed surface if I evaluate del cross f dot nds, then this will be equal to divergence of f deta, and this will be 0. This will be 0. And so the surface integral of curl of f over sigma is 0, and sigma since consists of s and s dash, so I can say this is equal to the surface integral on s and surface integral on s dash, which is 0. And from here I'll get an idea that del cross f dot nds on s is, I'll take this side, is equal to del cross f dot S dash, right? Now, what is the advantage of using this method? The advantage of using this method is I have converted a surface integral on a curved surface and written it in terms of the surface integral on a plane surface. See, it is always easier to evaluate the surface integral on S dash compared to S. We were asked to find this, but I have written this in terms of surface integral on S dash. Surface integral on S dash is easy to find. It's always easy to find surface integral on plane surface. How it is easy? What is the convenience you get on evaluating the surface integral on plane surface? First of all, plane surface, your ds is just dx dy. Your n is always lying in same direction on a plane surface. See, on a curved surface, n is not lying in same direction. N at every point lies in different direction. You can see it over here on S dash. First of all, let me find del cross f over here. Del cross f will be equal to I j k, and this will be d by dx dy, and this is x square plus y minus 4 3xy 2xz z square. So this will be equal to, there is no x component, y component is minus 2zj, and the k component is 3y minus 1, 3y minus 1 k. Now on S dash, your ds is dx dy, and what is n? N is always an outward or normal. Outward means outward from the volume, so n is minus k. So from here I can write f dot n is minus of 3y minus 1. Let me rub this portion. So ultimately your integral del cross f dot nds on S is equal to minus of del cross f dot n S dash, and on S dash we have ds equal to dx dy, n is minus k, and del cross f we have calculated over here. So and f dot n comes to a minus 3y minus 1. So ultimately this will convert to 3y minus 1 dx dy. This has to be evaluated on S dash. So the domain of this double integral is the region bounded by S dash, right? And what is this region? This region is x square y square equals to a square. Now this double integral can be easily evaluated in polar coordinate. We can use polar coordinate. First of all, using the property of definite integral, we will have some simplification. We can write it as dy dz, right? We write it as dy dz, and this can be written as dx dy, right? So what will be this integral? What is the limit of y? The limit of y is a square minus x square to minus of it. So what will be this limit? This integral equal to, this integral will be 0. Since you know the same thing, minus a to plus a fx dx is 0 if fx is a odd function. So this is equal to double integral dx dy, and this is nothing but area of the circle. So it is minus pi a square. This will be minus pi a square. So this is a very important type of problem where you convert a surface integral on a curved surface into a surface integral on a plane surface. This is very easy. This makes the problem very easy. Otherwise it would have been very difficult to solve the surface integral on this S, on the curved surface S. Now we'll move on to next question.